Okay, today we will discuss two important topics. They are shape of the atomic orbitals and also energy of the orbitals. First we will discuss the shapes and also probability plots of atomic orbitals. We have already studied about psi. Psi is a wave function, isn't it? And also about psi square, the probability density. That is the probability of finding an electron in an atom. It's the probability density and it's the square of wave function psi, or we will call it as psi square. Okay, psi is usually a mathematical function and has no such a physical significance. Okay, psi. It is a wave function. Okay, and the solution of h cap psi is equal to E psi will give you the energy values. That much only. Okay. For different orbitals, we can plot what psi, the wave function versus radius. Okay, radius of atom is a nanometer we usually measure, isn't it? Nanometer, we can plot what psi, wave function and also radius as a graph. Similarly, we know psi square. What is that? It is the probability density. That is, psi square at a point will give you the probability of finding an electron at that point. Also, that is called as probability density. Okay, psi square versus radius also we can plot for different orbitals. Okay, for different orbitals, psi square versus radius r will be different. Okay, and another point is what the region where the probability density psi square is 0 is called nodal surfaces or nodes. Okay, inside an atom, there are places or surfaces where the probability density or the probability of finding an electron is 0. That places are called what? Nodal surfaces. The region where the probability density function reduces to 0 is called nodal surfaces or nodes. And total number of nodes is given by the equation n minus 1, where n is what? The principal quantum number. Total number of nodes inside an orbital is n minus 1. Now, we will just refer to the plot of psi versus r radius and also psi square versus r radius. Okay. These are the plots of orbital wave function psi with radius. Okay, psi of r with radius. As I already told you, the wave function psi of r versus r radius has no physical meaning. Okay, this is just plotted graph of wave function psi of r with the radius. Similarly, for the oneness orbital, this is for oneness orbital. Okay, this is for oneness orbital, and then next one is for 2s orbital. Okay, 2s orbital. For oneness and 2s orbital, first is wave function psi r with respect to radius. Next is for 2s psi of r with respect to radius. Radius is a nanometer measured. Okay, that has no physical significance. Okay, next they plotted what? Psi square versus radius. Okay, psi square is probability density. Okay, the probability of finding an electron at a particular point inside an atom. So here you look, that has a significance, isn't it? We need to find where the electron is present inside an atom. Okay, Heisenberg uncertainty principle told we cannot find the atom's velocity and also position at the same time, but we can define the probability. Okay, where it can be present. A probability can be given. Okay, when we are drawing for oneness orbital psi square versus r, we can see what? Okay, consider this is an atom. Okay, this is the nucleus inside the atom. Radius means, okay, we are moving from near to the nucleus to the outside. Okay, moving from nucleus to the outer orbitals or outer side of the outer radius. So here we can understand what the probability density is high near to the nucleus. Okay, as the radius increases, it goes on decreasing and reaches 0. Isn't it? Okay, from here we understood that for 1s orbital, the probability density is more near to the nucleus. Okay, it is high near the nucleus, then it goes on increasing and reaches the 0, and it then goes in the same way, isn't it, as the radius increases. This is for the 1s orbital. Now look the case of 2s orbital, psi square value versus radius. Okay, the probability is maximum at the near to the nucleus itself. Okay, it goes on decreasing and reaches the 0. Okay, the probability of finding the electron here at a particular radius is what? 0. And after that what happens? It then also increases, reaches some maxima and then decreases. Okay, the probability of finding, if it is 0, then we will call it as the node, isn't it? Nodal surfaces is what I explained. Okay, first near to the nucleus the probability is very high for finding the electron. Then it goes on increasing at a particular radius. What happens? The probability becomes 0. Then it again increases. The probability of finding the electron again increases, reaches some maxima and then decreases as the radii increases. Okay, this is the meaning of this plots. Psi square versus radius. Probability density versus radius for 1s and 2s orbital. For 1s there is only what? It is more maximum near to the nucleus, but here, okay, near to the nucleus it is maximum, but also at certain point the probability of finding also then also increases. Reaches a 0 position, then starts increasing. At a particular radii it becomes a maxima and then goes on decreasing for the 2s orbitals. Like the plots we have already drawn, we can also represent orbitals with boundary surface diagrams. Okay, boundary surface diagrams. Okay, it's a good representation for the shape of orbitals. Okay, S orbital is, S subshell has how many orbitals? Only one, isn't it? Which contain 2 electrons. S. Okay, 1s, 2s. Contain only one, S subshell contain only one orbital with 2 electrons, maximum of 2 electrons. Okay, S orbitals are spherically symmetric. Okay, spherical in shape, and that means the probability of finding an electron is equal in all directions. Okay, they are spherically symmetric, or we will draw the boundary surface diagram of S orbital like this. Okay, like a sphere, they are spherically symmetric, that is, the probability of finding an electron is equal in all directions. And one more point is what? Size of the S orbital. Okay, 1s, 2s, 3s, etc. is there. As the principal quantum number increases, the size of the S orbital also increases. Okay, as consider this as 2s. Okay, 1s will be this. As the principal quantum number 1, 2, etc. it increases, size of the S orbital also increases. And as the principal quantum number increases, okay, the electron will be present more and more far away from the nucleus. As the principal quantum number increases, the presence of electron will be far away from the nucleus. This is the boundary surface diagram of S orbital. Now, moving on to P orbital. P subshell has 3 P orbitals, isn't it? We already studied that. 3p or P orbitals. Okay, P 1, 2. Isn't it? There are 3 orbitals. Similar to S, there is only in S subshell there is only 1 orbital. But for P subshell there are 3 orbitals. These, okay, this can be named as Px, this is Py, and this is Pz. Okay, so as subscript you can write Px, Py and Pz are the 3 orbitals of P subshell, Px, Py and Pz. Okay, all of them will have different boundary diagrams for Px, Py and Pz. Okay, the maximum number of electrons in S orbital was 2. But in P orbital how much? 6. 1, 2, 3, 4, 5 and 6. Maximum electrons that occupy in P subshell is 6. Okay. Now the diagram of Px orbital. Okay, what you should do is consider this as the x-axis. Okay, this as the y-axis and this as the z-axis. Okay, if you are considering like that, or here you can draw. Okay, this is the x, y and z. Px means in the x there will be, or in the x-axis. Okay, in the x-axis there will be electron density. Okay, so the lobes will be in the x direction or in the x plane. Lobes. Okay, similarly for Py. So for x it will be like this. Okay, for Py it will be in the y direction or y axis. This is x, this is y axis and this is the z axis. So for Py the lobes will be in the y axis and for Pz the lobes will be in the z axis. Okay, P orbitals are dumbbell shaped. Okay, they are dumbbell. This is the shape of a dumbbell, isn't it? So they are dumbbell shaped, we can say. P orbitals are dumbbell shaped. Spherical in nature is s orbitals. They are dumbbell shaped. P orbitals. Surface diagrams of d orbitals. That means d subshell contain how many orbitals? Already we studied, isn't it? D orbit or d subshell contain 5 d orbitals. That means 1, 2, 3 and 4. Okay, there are 5. 1, 2, 3, 4 and 5. 5 orbitals are present in d subshell. So what are they? We will name it as dxy, dyz and dxz. Dxy is the first d orbital. This is dxy. Okay, next is dyz. Okay, second one is dyz. Okay, subscript as yz. And the next one is dxz. xy, yz and xz are the 3 orbital. Next orbital is dx square minus y square and dz square. Okay, dxy, dxz, dyz and then dx square minus y square and dz square. Okay, now look at the diagrams. This first one is dxy. Okay, this is dxy. dxy. So the lobes are present in between the axis here. Okay. The p orbital lobes are present on the axis. Here in dxy the lobes are present in between the axis. For dxy, okay, in between x and y axis the lobes will be present. For dyz the lobes are present in between y and z axis. Look at the axis. Okay, both 3 of them are different. Means the axes are different. Here between y and z, so it is dyz. Here in between x and z, in between the coordinates x and z, so it is dxz. Okay, these are the first 3 orbitals. And next it is what? dx square minus y square. Okay, dx square minus y square difference is what? They are on the axis. Okay, between x and y axis. Above the axis the lobes are present, that is dx square minus y square. Okay, next dz square is the last of the 5th orbital. dz square, the lobes are present on the z axis and also in between that axis. Okay, like that it is shown. This is the surface diagram of dz square. They are what? Spherical. They are degenerate orbitals. They are 5 degenerate orbitals. Okay. They are 5 degenerate orbitals. That means they all have what? Same energy. This is the boundary surface diagram of d orbitals dxy, dyz, dxz and also dx square minus y square. So dear students, let's wind up today's session. Be happy and stay safe. Thank you.